Previously, we have discussed the IV characteristics of the bipolar junction transistor, and we found that one of the most important curves in the IV characteristics is the relation between the collector current IC and the voltage VCE. And we found that this relation basically it's a straight line for a certain value of I base. Let's say I base equals 20 microampere. IC will be constant up to a certain point called VCE saturation, and then it will start to decrease until it reaches 0. And the value of IC here, basically, we call this straight line, or we call this region where the collector current is just constant. We call it the active region where IC equals constant beta multiplied by I base. So if you fix I base, IC will be fixed, even if you increase VCE. So this region is called the active region where IC equals beta I base. At this point, the transistor starts to enter the saturation region where the collector current starts to decrease towards 0. At this point, it happens at VCE, at a voltage VCE called VCE saturation, which is usually between 0 to 0.3. Most of the time, we use it as 0.2, or depending on what will be given to you in the question. If we are talking about exams or quizzes, it will be given, usually it will be given to you in the question. But you should know that it's between 0 and 0.3, this value of VCE saturation. This value is the point at which the transistor enters the saturation region, and once it enters the saturation region, you will find that IC decreases towards 0. If you increase I base, then you expect that you will get another curve where IC will be higher, because IC equals beta I base. If you increase I base, IC also will increase in the active region. And again, it enters the saturation region approximately at VCE saturation and then decreases to 0. If you increase I base again, you get another curve, and so on. So that was one of the most important curves that we are going to use today in order to define the different modes of operation of the bipolar junction transistor. We are going to talk about the three modes of operation, the three important modes of operation. We said that we have 4 modes of operation, but one of them rarely happens in our circuits, or we rarely use in our circuits, which is the reverse active. So we are going to focus on only 3 modes of operation: the cutoff, the active, and the saturation. By the way, also, let's go back to the curve. If you decrease I base to 0, which means that the transistor, both junctions of the transistor, the base emitter junction and the base collector junction, both of them are reversed. There is no current in the base, basically. Then this is the point at which the transistor will be cut off. Okay? So what we are going to discuss here is the 3 modes of operation. If you assume any mode of operation, what equations you can use, and how you can check for whether the transistor is really in this mode or not. So for each mode, we are going to discuss what equations you can use by default and how you can check. So let's start with the cutoff. Cutoff means that the transistor is off, means that it's basically open circuit, which means that all the currents by default you can use that all the currents are 0. So you can use that I base equals IE equals IC equals 0. So if you want to assume or you guess that the transistor is operating in the cutoff region, then by default you can assume or you can use that all the currents are 0. I base, I collector, I emitter, all of them are 0 because it's off, open circuit. How can you check for this region? How can you check that you are really working in the cutoff region? In order to be working in the cutoff region, as we said a few minutes ago, both junctions must be reverse biased. So the base emitter junction must be reverse biased, which means that VBE must be less than the operating voltage of the junction, which we usually assume that a junction starts to operate at 0.5 volt. So VBE must be less than 0.5 volt, and also VBC must be less than 0.5 volt. So both voltages on both junctions, the base emitter junction and the base collector junction, both of them are less than the operating voltages, which is 0.5, then both of them are reverse biased. Both junctions are reverse biased. Okay? And you can apply this to any circuit, not necessarily the circuit that I'm plotting here. I'm plotting here a very simple circuit with one resistor, one supply, but you can use the equations and the check for any circuit where you have a transistor that you assume it's a cutoff. Same for the remaining modes of operation. You can use the equations that we are going to obtain and the check for any circuit. It's not necessarily for the circuit that I'm plotting, but I'm showing you this circuit just as an example. Okay? So for the cutoff, you can use that all the currents are zero, you solve your circuit, and then at the end you have to check that both junctions are reverse biased by checking VBE less than 0.5 and VBC less than 0.5. If you are in the active mode, or if you assume that you are working in the active mode, and remember that this is the collector, this is the emitter, this is the base. I base is in this direction, I collector here, and IE in this direction. Then in the active mode, we know for sure that IC equals beta I base. So you can use all the current equations, IC equals beta I base. And you can use that IE equals 1 plus beta I base. And you can use that IC equals alpha E. Same equations that we discussed in the physical operation of the transistor in the active region. And you can use the general equation, also the general equation, which is IE equals IC plus I base. This is the general equation that you can use in any mode of operation. But in the active, you can, in addition to this equation, you can use that IC equals beta I base, where beta is a constant, IE equals 1 plus beta I base, and IC equals alpha E, where alpha usually in the range of 0.99 or something greater than 0.9. Beta is between 50 and 200, and in some special cases it can reach to 1000. And as an additional information, beta here, beta and alpha, both of them, they are kind of temperature dependent. So as you will see in the lab, in one of the lab experiments, they change with temperature. They are not all the time constant. They change with temperature. They change with the value of VBE. So they are kind of not reliable. But in our course, in our theory, we assume that they are constant. Except that if I tell you that there is an early effect in the transistor, which we explained before, if I tell you that there is an early effect in the transistor, then you can adjust the beta to be beta multiplied by 1 plus VCE over the early voltage. In this case, beta will be dependent on the value of VCE. So if I mention to you in the question that we have an early effect with an early voltage VA, then you have to use beta, which we call here in this case beta F, to be beta which is constant. This is the constant beta, which is 100 or 50 or whatever, multiplied by 1 plus VCE over VA. So beta will be dependent on the early voltage and on VCE. Anyway, so if you assume active, you can use all these current equations. You can also assume, or you can use that VBE is 0.7, because we know that if you are active, the base emitter junction will be forward, so VBE will be 0.7. Or in general, it will be VBE forward, the forward voltage of the junction, of the base emitter junction. The base emitter junction is just like a diode. The forward voltage of it can be anything between 0.7 to 0.8, right? Usually we use it 0.7, but assume that in a question I can give it to you like 0.8, then you use 0.8. So here in the active region, you can use all these equations to solve your circuit. After you solve your circuit, how you are going to check? How are you going to check for your assumption? So in order to check for your assumption, you have to make sure that you are operating in this region. You have to make sure that VCE is greater than VCE saturation, right? Because in order to be active according to this set of curves, VCE in the active region, VCE is greater than this value, is greater than VCE saturation. So your check here will be that you check the voltage VCE. The voltage VCE is this voltage. This is the voltage VCE. You have to check that VCE is greater than or equal to VCE saturation. Of course, the equal sign doesn't matter because the critical point at which VCE is exactly equal to VCE saturation, this point can be considered to be active or saturation, and it is correct to assume it's active. It's correct to assume that this point is also saturation, no problem, okay? They will be exactly equal. This is the edge of saturation. We call it the edge of saturation. Okay, so this is your check. This is what you can use in order to solve your circuit, and this is how you check for that active region at the end. In the saturation, as you see from the curve here, in the saturation, IC starts to decrease below beta I base. So here in the active, IC was beta I base. Here, IC will start to be less than beta I base. Also in the saturation, we know that VCE will be something in the range between 0 and 0.3. However, for simplicity, we assume that in saturation, we assume that VCE will be constant, which is equal to VCE saturation. Although practically speaking, it is not constant, but we assume that approximately it will be like a vertical line here. It will be constant at a certain value between 0 to 0.3, and this value will be given to you, which is called VCE saturation. So in the saturation, if you assume that your transistor is operating in the saturation region, so by default, you assume that VCE will be equal to VCE saturation. What else? We know that in the saturation also the base emitter junction is forward, so you can use that VBE is also VBE forward, which is usually 0.7 volt. So you can use VCE equals VCE saturation, which is, it will be given to you, usually it's 0.2, okay? And you can use the VBE equals VBE forward, the forward bias of the VBE of the base emitter junction, which is usually 0.7. What else you can use? You can use the general equation for the current. The general equation for the current, which is IE equals IC plus I base, right? So you can use this general equation in addition to VCE equals VCE saturation, VBE equals VBE forward, which is 0.7. You can use these equations in order to solve your circuit, and then at the end you have to check. How can you check for the saturation? You have to check that you know in the saturation region that IC will be less than beta I base, right? So you have to check that after you solve your circuit, you have to check that IC must be less than beta I base, and this is the check that we have to do in order to make sure that we are really working in the saturation region. Sometimes they call this beta. Sometimes they call this beta. They call it beta force. The beta that or they call, sometimes they call IC over I base. They call it beta force. Beta force. So the ratio between IC and I base in the saturation region, it will be beta force, which must be less than beta. Okay, it's the same check exactly. I suggest you just stick to this check, but this is exactly the same, that you say that the ratio between IC over I base is less than beta. This ratio in the saturation, we call it beta force. So it's just a matter of naming, okay? But eventually this is the check that you have to do in order to make sure that you are operating in the saturation region. That's it for the three modes of operation. So we'll see later that you are going to use the assume solve check strategy that we used in the diode, in solving the diode problems. You are going to use the same strategy by assuming the mode of operation of the transistor, solving the problem, and then you check. So if you assume active, for example, you can use these equations to solve your problem. After you finish, you have to check that VCE is greater than VCE saturation. Assume that, or imagine that after assuming active and you solved the problem, you found that VCE is less than VCE saturation. then you know that your assumption was wrong. It was not correct, and you have to change your assumption. For example, you assume saturation, and then you solve the problem again using these equations, and then you check again to make sure that you are in the saturation region, and so on. So these are the three modes, three important modes that we are going to use in our course mostly. Okay, we don't deal with the reverse active mode, the fourth mode. We don't use it at all in our course, and that's why we focus on the three modes of operation. And then you will do the same strategy that we used in the diode: assume, solve, check. See you in the next video.